Hello, this is A. Schweitzer, and this is a little bit longer video on polar molecules. First of all, what is a polar molecule? Well, a polar molecule is a covalently bound chemical. I could just draw a circle like this representing a molecule, or maybe I could put like a X single bond to another compound, let's just say Y. And for some reason, electrons aren't being shared equally, and more electrons are spending their time by Y or by X than the other guy. So we end up with a slight negative side, say right here, and since the protons are locked in place and all electrons are spending more time over here, then this side is relatively positive. We commonly refer to this as a dipole. And if you want to quantify this value, we would refer to it as a dipole moment. So if we were bonding together two elements that were exactly the same, X bonded to X, then they would have the same pull on these electrons, and then the dipole moment, dPm, would be equal to 0. It's not something that we would usually quantify. We'd simply compare one versus another one. So there isn't a real common numbering system that we would use, but in some sense, it's still quantitative. So how does an atom become polar, or what effects does it have on it? That'll be my next slide. So in what ways do polar molecules affect the behavior of molecules? So let's just say, for example, that we have one molecule, and this thing has positives on, let's just go X going to Y. We have negatives over here, and we have positive over here. How does this charges on it affect its behavior? We're going to basically separate this into two different types of behaviors that we'll look at, and both of them are surrounded around Coulomb's law. Force equals charge of an item times the charge of an item divided by the distance squared. These charges are simply going to attract to other charges, and that's going to have some effects. One side I'm going to put here, it would be state of matter. This would be solid, liquid, or gas. And more specifically, we would probably be discussing it in terms of melting points. It would also have effects, so that's liquid going to gas, but that would be affected going to liquid to solid to liquid, but liquid to gas could be boiling point. But as a common reference point, maybe we just look at melting point. How does this work? Well, essentially, if you have a particle and it has a set of charges on it, it's got a dipole on it, one side's positive, one side's negative, then if you put them together, they will actually start to attract to one another, and we'll get negatives. So it'll be a positive on this side, and a negative over here, and of course then we could give another one that will lay on top here, which would be negative here and positive here. Another one here could be, just say, positive and then negative, and have another one here. So they start just clumping together, and they stick to each other. Now, the inside, a little reminder, inside this thing is a covalent. But between these two, there are interactions, which we call intermolecular bonding. And I would point right there, or even here, all through this between intermolecular bonds. Now, these bonds can be many different types. The most common one of intermolecular bond would be hydrogen bonding, and we can talk more about that later, but essentially all intermolecular bonds are based on a positive negative attraction. How that actually happens would specify the type of intermolecular bond. So how they get the positive and how they get the negative, that would be specifying the intermolecular bond type. Our other section we have here would be this side over here, and that was going to be solubility. Now, if I were to draw a picture of this, of course, solubility is how well something dissolves into a solvent. We got, let's just say we have a polar solvent, in which case we have hydrogen, hydrogen, negative, positive, and this is our solvent. Now, the solvent itself has charges. So if I were to drop this substance in here, negative, 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 and positive, 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 the negatives of this particular side will be attracted to the one side over here, which is the positive side, and then of course it will also be attracted to, let's say, the negative side of the other side over here. So oxygen here, hydrogen, and hydrogen. So there will be a definite attraction between the solvent and the solute. Okay, positives or negatives, positives over here. Either way, doesn't really make a difference how you want to draw it. Positive here, negative here. So that's your standard way of showing it. There is a phrase called likes, dissolve, likes. And this is basically saying if this has a charge, then this has a charge, then they would most likely dissolve in each other. If you write this down on an advanced placement exam, they will not accept this as a reasoning for why this substance dissolves in here. You'd want to explain the fact that they have charges and the water has a charge and the positive and negatives are attracting due to electrostatic attraction or Coulomb's law. That is the proper way of describing it. Obviously, if this solvent doesn't have any charges, well then there's going to be no reason why any positive or negatives would attract to it, and it would simply fall to the bottom as a solid. So there are lots of things. This is just a very small discussion of two things that we will use for explaining why do polar molecules affect the behavior, in what ways do polar molecules affect the behavior of molecules. So these are some major effects. There are other things as well. I'll also point out that as we move forward here, this is just a very brief overview, and you would definitely need to watch the PowerPoint on this topic, be able to work through some problems, and it gets a little more complicated, so make sure you understand this is not everything. It's just a brief overview, and I'm not going to spend a lot of time overly explaining things. You get a brief overview, and then we're going to move on. And some of that stuff we talk about, you still need to master as you move forward. So how does a molecule become polar? So at some point, we need to have the electrons get dragged over from one side to the other. That is going to be a term that we're going to call electronegativity difference, or at this point, I'm just going to call it electronegativity. And atoms attraction for electrons in a bond. Now, in this case, these two atoms right here are essentially playing a little game of tug of war, where one atom's pulling, the other atom's pulling, and in this case, they're not wanting to share equally. We could have a situation where we have two atoms, like I drew earlier. If they're the same atom, well then obviously they're going to have the same electron activity, and therefore it's going to be a bit of a stalemate, and we're going to have a dipole moment of 0. And another way of saying this type of bond is a pure covalent. Dipole moment of 0, not polar. This one, negative, 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 positive, positive, positive. Okay, this is a generic example. X and Y do not exist. Just two atoms, one which Y has a larger electron activity than does X. Okay, and again, think about how I just explained that. Y has to have a larger electron activity than X. So there is another aspect to this thing where it's called electronegativity difference. That is, you take and you subtract two atoms' electronegativities. So And in this case, you know, each of these guys would have their own individual electron activity. Now, you wouldn't necessarily want to memorize the electron activities. They'll be given to you on a chart, but you should have some general idea about which atoms have high electron activity and which ones don't. So on the left-hand side here, I'm going to draw out a little periodic table and show you the general trend. This is the lowest electron activity. Fluorine is the highest. So it increases as you go to the upper hand corner. Now, I often refer to electron activity as a stealer. There are 3 or 4 atoms that are extremely high in electron activity, and when you put them with other atoms, they tend to steal electrons. Stealer is not something you'll find in a textbook. It's just something that I tend to phrase. And kids are told that on an advanced placement exam, you would not want to use the word stealer. You need to explain that it's just a highly electronegative atom bounded with some other lesser electronegative atom. These atoms are nitrogen, oxygen, fluorine, and chlorine. On the Linus Pauling scale, nitrogen and chlorine are the same. Linus Pauling is a scientist that came up with this idea and gave values for each of these. Either way, anytime you get one of these guys paired with some other atom, we'll have an unequal sharing of electrons, and that hence causing a dipole. Example might be for NH3, which is ammonia. Now ammonia, we check each bond individually. Okay, now they're all the same. So in this case, nitrogen is highly electronegative, hydrogen not so much. It will be causing the electron to be drawn towards this direction. This is actually a little notation we might use where this means negative, this means positive. It shows the direction which the electrons are moving. Now this will move towards the nitrogen. Another example might be, let's say, obviously H2O is another example that still holds this. We got some unbonded pairs here, but either way, the highly electronegative, not so much. And electrons pull in this direction, pull in this direction, making this region positive, this region negative. Again, if we were to take F2 and put them together, this would be a stalemate. So it's kind of a tug of war. You need one of these big bullies and one that's maybe a little weaker. This would be canceled. This would be a nonpolar substance. Even if we did this, okay, this would be a compound that is going to be sharing more equally than, let's say, like NH3. Okay. All right, so does a molecule have polar bonds, or does it at some point have a dipole? Well, that means somewhere on the molecule, and molecules can be very large. You only really need to have one dipole for this thing to express some amount of polarity. So at some point, big molecule, small molecule, we need a nitrogen or an oxygen or a fluorine or a chlorine to bind with some other atom, not one of these guys. If we don't have this, then we're not going to have unequal sharing of electrons, and we will be, this is no, we don't have that, then we're going to be non-polar. Okay. Now, going this way, the answer is yes. Okay, we have one of these. All right. Then are we guaranteed to be polar? At this point, still the answer is no. We have one more aspect, which is called symmetry. It's possible for an atom to be equally dragging electrons in all different directions, not leaving one side positive, one side negative. For example, we have water, where water happens to be bent in shape, where this side ends up being negative, this side ends up being positive, as opposed to a molecule, let's say like carbon dioxide. Now carbon dioxide looks like this. Okay, now it's kind of like, again, like a tug of war. Is there any one side that wins out? Well, no, because yeah, we have electrons pulling in this direction, and we have electrons pulling in this direction, but we don't get any one region that's positive or any one region that's negative. It has to be kind of lopsided. We use symmetry as a means to try and see, is a molecule symmetrically lopsided? Is it symmetrical or is it lopsided? Now this is a symmetrical molecule. So if we have these polar bonds, but they're equally divided in all different directions, so we're symmetrical, the answer is yes, okay, then those charges cancel, or the tug of war cancels out, and we are nonpolar. Or if the answer is no, we are lopsided, then we are now have charges, there's nothing to cancel them out, and we are polar. Okay. Now, spending time looking at polarity is difficult because it involves a three-dimensional description of what's going on. Now, I would say that there's lots of information on that PowerPoint about this. There's pictures, there's animations in order to try and make things more visual. Right here is a handout that you have. This is taken from the internet. It shows all the different shapes and things you want to know about them. Okay, this is in your workbook. But from this, if I want to summarize this, and I'm not going to give every single name of every single shape. We will do that in class, and if you miss class and you want to go over it, you need to come and see me. But we essentially have 5 shapes. We also did a Pogo activity about this, so it should start to hopefully click a little bit. But we have 5 shapes. We have our central atom, I'm going to use as an X. So 1, 2, 3, 4, 5 different atoms. And I'm going to have the central atom be the main, well, the central atom always is what's determining the shape. So if we have just 2 things coming off the center, I'm going to just call them element circle, then electrons don't like each other. There's electrons around here, there's electrons around here. They don't like each other. They're pushing away from each other as much as they possibly can. And this is called the valence electron shell repulsion theory. Basically says that because these are negative, they don't like each other, they repel, and it will get as much room as possible. This thing right here is, let me just give myself some room here to cloud my, okay. This shape is called linear. And as you can see, it forms 180 degrees. All right, so if we have a third item coming in here, and this is going to start getting a little bit more difficult as we start drawing them, it forms a shape called trigonal planar. Okay, and I'll put a little smiley face by the ones that are symmetrical. This is obviously symmetrical. This is in a plane, so it's flat, all in the same plane, and they're all canceling. There is 120 degrees, much like a bicycle tire, and yes, this one is symmetrical. Okay. In fact, every single shape itself starts symmetrical. So whether I put a smiley face on it or not, I guess it really doesn't matter, because that is one reason why I want to talk about all the individual categories, is that they start out symmetrical. What happens is, as you lose pieces, and I will show you in a moment how this works, that's when they become lopsided. So every major classification of shapes starts out symmetrical. 4 things, 1, 2, 3, 4, like a pyramid. Okay, this is going back a little farther, coming up front. Okay, it's called trigonal. Made a mistake there. It's not trigonal, it's tetrahedral. I just did trigonal. Tetrahedral. Okay. All of the angles are 109 degrees. 109.5, I think is technically what it is. Now, the next one is going to be where 5 things come off the center. We're going to go, the equator is going to have 120 degrees, and then we're going to have one going up and one going down. So these are all my different atoms around the center. This angle here is 90, and of course it's symmetrical. Like I said, they all start out symmetrical. The 6 things off the center, actually I should say the name of this shape, it's trigonal bipyramidal. Okay. And then the last but not least, 6 things off the center. We got off the equator, and again, it's harder to see, but up and down. These are all on the equator, and everything is 90 degrees. So no matter where you are, its angle is 90 degrees. All right, so let's just kind of take a few of these and kind of look them over a little bit. I'm going to look at the trigonoplanar one here for a moment. Okay, and let's take a look at how this becomes symmetrical to being non-symmetrical. So we have trigonoplanar. Okay, now all right, so when you're doing your Lewis dot structure, you would have essentially this thing here, x, O, 3, and it would look like this, x, O, O, and O, all right? And there would be actually no more extra pairs on the center atom. So this is a little unique. An example might be boron trifluoride. That would be something that would follow this particular atom. So this is violating the octet rule, just so you know. But we'd have electrons over here. Of course, these outer electrons are not affecting the shape. Well, they are by repulsion, but the center atom is kind of how we govern that. This is called trigonoplanar. Okay. Now, what if we had something that looks like this? XO2 turns out like this. Okay. Oxygen, oxygen. I guess I don't call them oxygen, but we have an empty pair here. It just turns out that way via your Lewis dot structure. Now, in this case, turns out that this pair takes up, anytime you have an unbonded pair, it takes up more room than does if there's actually an atom there. There's a little more repulsion as you go down, so this angle here is a little bit less than 120. Like I said before, these are 120, so maybe it's 119. It doesn't really matter. It should be slightly less than 120 degrees. You should be aware that extra pair squishes it down. The name of this shape, because we don't see this pair in real life, it's kind of invisible, you might say. It doesn't show up with the family picture. All we have is this. And we give it a real technical name called bent. Okay. And this, of course, is not symmetrical. This one, yes. This one, well, no, it's not symmetrical. If these are highly electronegative, it's going to draw to one side versus the other. Let's go to, even just walk through all of these, but we have the next shape is 4 things, which is tetrahedral. And the tetrahedral shape is much like a pyramid. It's hard to draw that shorter, looks like it's going farther away from us as it's coming straight up. So an example of this one might be CH4, which is methane. 109 degrees, it's symmetrical. Now, we draw another molecule, might be, let's say, NH3. So we have the nitrogen in the center. We have hydrogen, 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 and there's a lone pair on top. Okay? This is called trigonal pyramidal. Okay, and again, this will take up a little more room, so it's going to be squeezing these guys down ever so slightly to a little bit less than 109 degrees. I think the exact might be 107. Again, not too important, just know that it squeezes it down. What if we have, next example would be 2 missing pieces. This would be how H2O works. Oxygen in the center, 2 unbonded pairs looking like this right here. Okay, so now we have unbonded pair, unbonded pair. It still follows the same geometry as this guy does. It still has the same geometry, 4 things off the center. Just so happens that 2 of those things are obtained or occupied by unbonded pairs. So we once again call this thing bent. These do not show up. We get an angle here of about 105, so it's a little bit less than even the 107 for that guy. Not something you need to know, just know that it's less than 109. If we move on to, let's say, the 5 bonds. And I will also point out that this guy is not symmetrical, and this guy also is not symmetrical. Things start out symmetrical, and they end up being, as you lose pieces, become asymmetrical. All right, so 5 bonds off the center. Okay, and this is going to start as a trigonal bipyramidal. All right, and here we go. We'll just draw some pictures of these guys out. It'll be X, O, 5. Draw your Lewis dot structure, and it turns out to look something like this. I'll have all the angles marked out already, and we should note that this is symmetrical. Okay? Its name is trigonal bipyramidal. What happens if we have one where XO4? Now, as you look at this, you might think, this looks like tetrahedral. We got a central atom, 4 things around the outside. But when you do the Lewis dot structure, it appears that it looks like this. And you have 4 things on the center, and your extra pair goes on the center. So whenever you're doing a Lewis dot structure and you have extra electrons, they go on the central atom. So it turns out that this central guy here has an extra pair. I put it over here on the equator. So it's sort of following like this. Bond, bond, extra pair, and then one going up and one going down. It's following the same geometry as this guy. This is not symmetrical, and we call this seesaw. If you rotate it to the right a little bit and tip it, it looks like kind of like a seesaw, meaning like that. Okay, seesaw. Okay, not symmetrical. Angles are what they were. It's about 120, a little less between here, and about 90 from those guys. Vertical axis, equator around the outside. Again, a little hard to see in a 2-dimensional space. Moving down a little bit, we can actually take another pair off, and it will look like this, where we have our central atom, one going down, one going up, and of course we lost another pair. And again, it came off the equator. This is called T-shaped. Okay, it's mimicking sort of a shape of a T. Okay, this is not symmetrical. Angles would be pretty much 90 here. One equator left to the axis. Our last one, XO2, means we have now lost every one we have off the center. We still have our vertical, one going down, and we just call this thing, once again, linear. It's a different linear than the last one, but nonetheless, it is 180-degree angles, and it is symmetrical. Flipping over to the 6 bonds. Example here would be SF6 sulfur hexafluoride. Sulfur's in the center, and it looks like this. 6 seems to be the most things I've seen bonding off one center. These are all the equator up and down, but they're all equally spaced at 90 degrees, and this thing is symmetrical. Take one off, we'd have XO5, and we have X in the center. All of our original equators are intact, and we are going to lose one off the vertical. We call this square pyramidal. Again, angles get pushed up slightly. It is asymmetrical. And finally, our last one here, we have XO4. Again, it appears like this thing could even be tetrahedral. But when we're doing our Lewis dot structure, we find that we have a few extra electrons left over, and those get put on the central atom. Turns out to be the vertical axis gets removed, and this thing is just one big flat equator, and they call it square planar. So from this, what we would want to be able to do with this thing, all this information we now have, is do we want to be able to determine if an atom is in fact going to be polar or not. For example, if we did, let's say, SO2, sulfur difluoride. So in this case, first thing we'd do is, it's okay, let's draw a Lewis structure of this thing out. Sulfur, oxygen, oxygen, okay. This guy's all going to contribute 6 electrons towards the valence for a total of 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So they're missing 1 pair of electrons here. So I'm going to erase 2 of them and form myself a double bond. I, of course, would want to draw a resonance structure here. Just so you're aware. And there we go. All right, is this thing polar, is it not polar? The first thing we'd do is we'd say, okay, well, is there a polar bond? Do I have a stellar or a highly electronegative atom bonding to one that's not? And the answer is yes. I have an oxygen here bound to some non, but it's on both sides, which is fine. So I have a dipole moment going this way and a dipole moment going that way. Okay. Now, what shape does this thing have? Is it symmetrical? Are these canceling? I've drawn it in a straight line. But you should realize there are 3 things coming out the center. I have the sulfur, I have an unbonded pair, and this is going to form a trigonal planar shape, where this is 120 degrees, 120 degrees, and 120 degrees. Now, I said 120, but it's a little less. That's a little bit more repulsion than what you might think. So it's actually a little less. This is a little less than 120. I'm not too concerned about that at this point. I just want you to realize that it is, in fact, a bent molecule. So, 1, do we have polar bonds? Yes. These areas will be negative. These ones will be, this will be positive. Is it symmetrical? Are these things canceling out? No. This is a region of negative. This is a region of positive. And I have a polar molecule. This content should be followed up with a bunch of practice problems and getting questions you have answered. Just let me know if you have any questions.